Hear me? Yeah, okay. So today I will be speaking about homomorphic encryption and especially how my colleagues and I managed to design an 8-bit processor that works over encrypted data. So just a quick reminder for those of you who weren't there for the invited talk. Homomorphic encryption allows computation to be performed directly over the encrypted data. And it's, for example, very useful to ensure the confidentiality of data sent to a distant server for computation. So in a word, it's great. And an encryption scheme is said to be fully homomorphic if it provides an unbounded number of both additions and multiplication in the ciphertext domain. For this work, my colleagues and I decided to work with a fully homomorphic encryption scheme called TFHE. The common use of TFHE is to decompose the messages into bits that we then encrypt and work on. And most TFHE state-of-the-art use this method because it has several advantages, such as the size of parameters, which allow somewhat efficient computations. And any computation can be expressed as a Boolean circuit only composed of AND and XOR gate that can then be evaluated in the homomorphic domain. So any computation is possible in the homomorphic domain with this method. For instance, if you want to homomorphically compute the addition of two encrypted bits, then you just take the correspondent Boolean circuit that I have put here, and you just perform it in the homomorphic domain. So this method is universal, but it also comes with some efficiency bottlenecks. For instance, I've put here the Boolean circuit corresponding to the addition of two 8-bit messages. And you can see that it will take significantly longer to evaluate this Boolean circuit in the homomorphic domain than just evaluating 8 times the addition of 2 bits. And this is only to perform a mere addition. So when you want to perform a full algorithm, then the corresponding Boolean circuit easily begins to look like this. And so to avoid this spaghetti effect, my colleagues and I decided to try to go beyond this Boolean approach and thus to work directly over encryption of integers. So a little background on TFHE. TFHE works with a rather small plaintext space, but it has a very powerful bootstrapping, which made us choose this encryption scheme. And TFHE proposes 3 structures to encrypt messages, but I'm merciful and I only present one, which should be enough to understand the presentation. So the type of ciphertext I present to you is called TLWE. It's the simplest one, and it allows you to encrypt one value of the plaintext space. So all you need to know is that at some point during the encryption process, we add a noise E to the message, and this noise will grow with every operation that is performed on the ciphertext. So after several operations, the decryption process may fail if the resulting noise of the ciphertext exceeds half the distance between 2 elements of the plaintext space. So to avoid incorrect decryption, TFHE proposes an operation to reduce safely the noise of ciphertext, and it's called bootstrapping. Okay, bootstrapping. So it relies on 3 building blocks that I present here. The first one is blind rotate, which rotates a clear text polynomial by an encrypted input, that is to say our TLWE ciphertext, and it returns it as an encrypted polynomial, and that's why it's in orange here. And I must stress that this step, the blind rotate, is by far the most expensive step of bootstrapping. Okay. Then we can perform sample extract, which extracts a coefficient of an encrypted polynomial and converts it into a TLWE ciphertext. And finally, we use the key switch to go back to the initial key, the blue key. So at the beginning of bootstrapping, you have a message M with a a dangerous noise, and at the end of bootstrapping you have another encryption of the same message M, but with a lower noise. And in fact, you can see that bootstrapping is like making a selection of coefficient in a clear text table, that is to say our polynomial's coefficient, using an encrypted index. So this being said, in fact, you can use any table you want, so why not the lookup table of a function you would like to evaluate? For instance, if f is the function you would like to evaluate, you will replace the coefficient of your starting polynomial with those of the lookup table of f, just like this. And when performing bootstrapping on this new polynomial, you obtain an encryption not of m, but of f of m without any additional cost. So this operation is called functional or programmable bootstrapping, and it allows you to evaluate any univariate function over encrypted data. So it's great, and of course we used it, but for our processor we also wanted to be able to perform multivariate functions, and especially bivariate functions. And to do so, we need a bootstrapping method that allows us to bootstrap on several encrypted inputs. And that's why we choose to work with the tree-based method. So the best way for you to understand it is if I give an example. So here it is. In this case, we are working with 2-bit messages, and we have two ciphertexts, C1 which encrypts 1 and C2 which encrypts 2. And we want to homomorphically compute the addition of these two ciphertexts, but using programmable bootstrapping. So the first thing to do is to create the lookup table of the function we want to evaluate. In this case, it's pretty easy. It's just the addition of two 2-bit values. And we call this lookup table let_add. And then we divide this lookup table into 4 polynomials, P0, P1, P2, and P3. And you can see that P0, in fact, encodes a univariate function, which is +0. And P1 is +1, and so on. And then we can perform bootstrapping on this polynomial with selector C1, which gives us 4 new ciphertexts that we combine together to create a new polynomial. And you can see that this new polynomial in orange is, in fact, the function plus C1. And then we can perform bootstrapping on this new polynomial with this time selector C2, and it gives us an encryption of 3, which is what we wanted. But you remember that I said that blind rotate is very expensive. And here we have 5 bootstrapping to perform 1 addition. So it's not really efficient. And this is why we decided to use the multi-value bootstrapping optimization, or MVB. It's an optimization that allows you to perform several bootstrapping at the cost of only 1 blind rotate, as long as it's with the same encrypted input. So, for instance, we can use it here in the first layer of the tree, and instead of doing 4 blind rotate, we will only do 1, and we will perform the addition at the cost of only 2 bootstrappings. So the implementation of this optimized tree-based method, we called it let_eval. But you can even go further if you want to evaluate several lookup tables on the same encrypted inputs. You can factorize each first layer of the trees and then just continue each tree sequentially. And this implementation, we call it mv_let_eval. So at the beginning of the presentation, I said that we wanted to work over 8-bit values, that is to say values between 0 and 255. But secure TF-HE parameters for this plain text space are very large and do not allow fast bootstrapping at all. So we had to break our messages down in a smaller decomposition basis. Smaller decomposition basis different of 2, of course, because we don't want to simulate the Boolean approach. So from 8-bit messages, we have 3 decomposition bases, basis 16, basis 8, and basis 4. And of course, the smaller the decomposition basis, the smaller the parameter, and thus the faster the operation. But on the other hand, the smaller the decomposition basis, the larger the number of digits in the decomposition, and thus the greater the number of operations to perform to recover an 8-bit value. So a trade-off must be achieved between the number of bootstrapping and the parameter size of the decomposition basis. And to find which was the best trade-off, we did a benchmark of our lookup evaluation tools, and we choose to work with basis 16. I think it's pretty obvious why. You can see that it's the most efficient for our lookup table evaluation tools, but not only is it more efficient, it also outputs more data. So why is that? For instance, you can see MV star is the evaluation of 2 different lookup tables using the MVB optimization. So it outputs 2 values in the corresponding decomposition basis. So when we perform this in decomposition basis 16, we obtain 2 4-bit encryptions, that is to say the equivalent of an 8-bit value. But when we perform MV stars in basis 4, we get only 2 2-bits value, that is to say the equivalent of a 4-bit value, which is less than an 8-bit value. So this is why basis 16 is as advantageous as any other decomposition basis, and we of course used it to design our processor. And using decomposition basis 16 and Letival and MV Letival, we were able to design some 50 instructions, among them some usual FHE instructions such as addition and multiplication, but also some unusual FHE instructions such as division, conditional selection, or bit shift. And I will explain to you how we manage it. But first of all, a bit of specification to ease the rest of the presentation. So we denote with double brackets the set of all valid encryption of a message M. And we use uppercase letter to denote 8-bit messages. So if this uppercase letter is a C, then it's the encryption of an 8-bit value. And similarly, we use lowercase letter to denote 4-bit values that we also call nibble. And if this lowercase letter is a C, then it's the encryption of a nibble. So just a small example, we have a message here decomposed in basis 16. H is the most significant nibble and L is the least significant nibble. And the corresponding ciphertext is C, which is composed of 2 nibble encryption, where C0 encrypts H and C1 encrypts L. So if you manage to remember this notation, I think what follows will be pretty easy to understand, at least I hope. And I propose to start with hello world. So let's try to perform a simple operation, that is to say XOR of 2 8-bit ciphertexts that are C and C prime. That is to say we would like to obtain a third ciphertext whose encryptions are encryption of H XOR H prime and L XOR L prime. So the first thing to do is to create the lookup table that we will need during bootstrapping. In this case, it's very easy again. It's just the XOR of 2 4-bit values, so nothing difficult. And using this table, we can compute the XOR of our ciphertext by firstly compute the XOR of the most significant nibble and then the least significant nibble, and we indeed obtain an encryption of C XOR C prime. Okay, let's do something a bit more challenging, like the addition. So this time we would like to homomorphically perform the addition of C and C prime. That is to say, obtain an encryption of 16H plus L plus 16H prime plus L prime. So, as usual, the first thing to do is to create a table. And this time we need 2 tables. Because when you perform in clear text the addition of 2 nibbles, well, a carry may be created that you need to propagate to obtain a correct result. So we need not only the table that gives us the addition of two 4-bit values, but also the table that gives us the carry that is created. And this is why we need two tables. And with these two tables and our lookup table evaluation tool, we can compute the addition. We begin with the least significant nibble. We add them together, and we don't forget to compute the carry. Then we can add together the most significant nibble, and we do not forget to add the carry to the most significant nibble sum. And this gives us the addition of C and C prime. But sometimes the user knows that at least one of the two ciphertexts is an encryption of 0. And when one of the two ciphertexts is an encryption of 0, it means that there will be no carry to propagate. As this is FHE, we really try to be the most efficient, so we proposed an FHE-friendly add Z instructions that perform the addition when there is no carry. And indeed, we implemented matpantera to be sure that every optimized instruction possible is in there. And you can see that most of our instructions take less than a second to half a second, which is better, to evaluate. But for some complicated instructions, such as the division, which is notoriously difficult to compute in FHE, it can take several seconds, but at least we can divide. Okay? And with this set of instructions, we can implement any algorithm. So let's take a look at some of them together. For instance, we can compute the square sum of an encrypted array. So you can see that the algorithm is really similar to the one we use in cleartext space, but instead of using cleartext instruction, we use our FHE instructions. We can also propose the implementation of a bubble sort on an encrypted array. So this time, obviously, is not as easy as in the cleartext space, but we can still manage it thanks to our CDUP and NCDUP instructions that are, in fact, conditional duplication, which allow us to emulate if-then-else conditions. And so we did several algorithms. Also, we can do a sigmoid on 16-bit fixed-point arithmetic values. Yay! So I will not give the details here because it seems complicated, and to be honest, it is a little complicated. But you can check the paper for more details. But just to say, we can really do great stuff. Okay, so as I was saying, we evaluated several algorithms on encrypted arrays of different sizes. And you can see the result, the execution timings in seconds. So, okay, compared to cleartext evaluation, this might not seem like high performances, but for FHE standard, it's quite competitive. And just to be sure our intuition that it was competitive was correct, we did some comparison with circuit Boolean approaches state-of-the-art. So these are all circuit Boolean compilers. And you can see that for algorithm with a small Boolean circuit that, let's say, only use comparison, such as maximum or bubble sort, our approach is not the most efficient, but I would like to say that it's also not the worst. But as soon as the corresponding Boolean circuit grows a bit, that is to say, as soon as there is a multiplication or a more complicated instruction, then our approach becomes the most efficient of all. And just to check if it was also true at the instruction level, we took the more competitive approach to ours, that is to say Chingulata, and did some more comparisons. So you can see that first of all, we had to implement the division with Cingulata, which wasn't natively in the compiler. And you can see that for cleartext, ciphertext division, div-I, and ciphertext division, our approach is the best. For the addition, Cingulata is a little faster, but again, for the multiplication, Matpantera is really the best. And I've put again the execution timings of our set of algorithms, but I've added the number of blind rotate, which is NBR for Matpantera and NBR prime for Cingulata. And why is that? It's because the number of blind rotate in Cingulata is equal to the number of Boolean gates to be performed. And this explains the timings needed for the sigmoid. But our experimental results show that our approach amortizes the higher bootstrapping cost of integer mode and outperforms state-of-the-art compilers on instruction and algorithm that require a large number of Boolean gates, of course. And that's a conclusion, and I will leave you with some key takeaways. So we propose 2 generic tools to implement any operation. These tools are Latival and MVLatival, and with these tools we managed to implement a large set of instructions, including difficult FHE instruction and FHE-friendly instructions. And I've not talked a lot about it, but our approach also works for other type of ciphertext, mostly signed messages and 16-bit fixed-point arithmetic messages. We did the sigmoid with these kind of messages, and we even were able to implement a full neuron, so it was nice. And about perspective, we would like to always improve our processors, so maybe with some software optimization or hardware optimization. And also, of course, it would be a good idea to look at other values for the bootstrapping, just to consider the recent CPAD attacks. And that's it for me. Thank you very much for your attention, and I would be happy to answer any question.
Thank you. Are there any questions from the audience? We have time for one quick question.
Thanks for the wonderful talk. I'm not a big fan for TFHE, but after your talk, I changed my mind since they can process 8-bit. Okay. So is there any, what is the main bottleneck if you want to go beyond 8-bit, like 32-bit? Is it the complexity will grow exponentially or how?
Your question is, what is the, at one point, is it more interesting to take our approach than the Boolean one?
No, I mean, previously I'm not a fan of TFHE, but now I think it is quite good. But my concern is that going beyond 8-bit, is the complexity, it grow very fast, or it is still a linear complexity? Because when I see you use the 3-bit method, probably your complexity will be very big if you go to 32-bit.
I'd say it depends on the operations you want to perform, because you've seen that the XOR is very easy to do, and the addition is a bit more complicated. And of course, the multiplication is even more complicated, and so on. So really, it depends on the instruction you want to implement.
Okay. So is there any plan to go beyond 8-bit?
Yeah, of course. We really, as I said, we would like to do some software or hardware optimization.
So if there are no further questions, then let's thank the speaker again. And next up, we have a talk on how sharing shares can help us decrease the ciphertext sizes. And the talk will be given by Jean-Baptiste. So maybe while we wait for the technical problems to be resolved, I want to take the time to do an announcement about the excursion, since we have time now. If you would like to join the excursion to the craft complex, please proceed to the lobby starting at 3:15, but probably we'll still hear the talk by then, hopefully. The last bus will depart at 4. The excursion, including travel time, is expected to take less than 2 hours. Usherers will be waiting in front of the elevator to direct you to the main entrance. So if you are interested in, then head directly to the main entrance after we're done here with the session. Thanks. Okay. So it's like the problems are resolved, so let's go ahead.
Yeah.
Without delay.
Thanks. All right, so let's go for a super fast presentation of everything. So this is joint work with Loris Bergera, Charlotte Bond, Benjamin Curtis, Pascal Paillet, Samuel Tapp. And so the goal in here is we're trying to build batch bootstrapping for TFHE. So I'm going to be super fast on the introduction, FHE, blah, 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 cryptography paradigm, you know what it is, right? So we have the possibility to compute everything over encrypted data. It's pretty nice. And so all of this magical stuff is possible because we have like one cryptographic assumption, which is called LWE, for learning with errors. So I'm going to detail a bit that. So the idea is like we have a ciphertext, which is in 2 parts. So there is a part, which is called the mask. This is basically like pure random values that has been drawn randomly. And then there is the B part, and the B part is simply composed by the inner product between the mask and the secret key. And from this, we are going to add the things that we would like to encrypt, so our input data, so the message M in here, and then we're going to add some error, and the goal of the error is to ensure the security of learning with errors. And so basically, the assumption tells us that if I give you that, or if I give you pure randomness, you're not able to distinguish between both. And that's where the security should come from. In this talk, we are going to follow up what Daphne has presented previously, meaning that we are going to work over the TFHE scheme. So there are many schemes to do FHE. And the thing is, like, FHE is possible because of one operation, which is called the bootstrapping. So the goal of the bootstrapping is to be able to reduce the error. So you know, like the previous term, we have just added to all of our ciphertext. And the thing is, like, when we're going to do more and more computation, this noise is going to grow until the point where the correctness is compromised. And so the idea with the bootstrapping is, like, you are able to reduce this noise. So this is the magical part. And in the case of TFHE, this is also, like, the specificity of the scheme. Like, we are able to compute any univariate function over the plaintext of our choice, over the ciphertext of our choice. And so that's the magical part in there. And the thing is, this comes with no supplementary cost. So just reducing the noise or reducing the noise and compute the function, this is the same thing. However, there is no magic in here, and there is like a huge constraint that Daphne has pointed out before, is like we are forced to work with small ciphertext, like plaintext size, sorry. So the thing is, like, I want to encrypt things, and the maximum size that I can encrypt and then compute a programmable bootstrapping over it is like around 10 bits. And past this, or there are some impossibility, or this is way too slow to be practical. And so the thing is, in general, we would like to work with some stuff that are a bit larger than, you know, just 10 bits. In general, like in our programming languages and our day-to-day lives, we're working with 32 bits or 64 bits values, right? And so we would like to mimic this kind of thing. And so one of the way to do that is just to split your plaintext in many chunks, and then you are going to encrypt independently all of these chunks in LWEs. So in the end, I'm going to have, like, for instance, for a 64-bit ciphertext, I'm going to have like 32 ciphertexts because I have like splitted my plaintext of 64 bits in many chunks of 2 bits, right? So in the end, like, I have 32 ciphertexts, which is quite big. And so from this, we are going to mimic all the arithmetic over this kind of integers, because you can see this like as a big vector, and like you want to do additions, multiplications, all this kind of thing. And we can do this, and basically I'm not going to go into the details in there, But the thing is, if you want to do any operation, then you're going to need to compute many bootstrappings. And so that's a little bit like our assumption in there. So we are going to have many ciphertexts on which we want to compute many bootstrapping. And knowing that we have this kind of thing and data representation, this is what I mean by things, can we do something which is a bit better? And so the idea, when we think about that, is like, can we try to construct such a batch bootstrapping, knowing we have this kind of data representation? So of course, our goal in here is to first be faster, because the goal in here is like we try to have a better latency and this kind of thing. We want to improve the practicability of FHE. And the second thing is like we don't want to destroy the freedom that TFHE is offering, meaning we are able to compute any functions or any ciphertext. And so we want to keep this, and we want to be able to have like, even if we have many, many data, we want to be able to compute any functions on any chunks of data. That's the thing. And so, spoiler alert, in there, so we are going to construct such a bootstrapping, and we are able to go twice faster, and we also are able to have like one function per message. Okay, so let's go a little bit over another assumption that we are going to use, but first, let's keep having a look to LWEs. So LWEs, this is the basic way of encrypting everything with TFHE, right? So we have seen it before. The way the LWEs are constructed are like, I have a mask and a B, which is the body, right? And so if I have multiple LWEs, then I'm going to have like many masks. Is it working? Yeah. So I'm going to have like many masks, and meaning that for each of my messages, then I'm going to have like a different mask, so different random values. And for all of this, the common point is like we have only one key, and this is one key that is used to compute all the ciphertext, right? And so what we are going to do in here is switch a little bit this and say, okay, we want to compute multiple things. Let's try to make kind of a dual of or a revert way to see this kind of thing. And so the idea is like, I'm going to have a mask, I'm going to have a key. This is for one message, so this is exactly the same thing. However, if I'm adding new message, I'm going to use another assumption, what we are calling common mask or CM in the rest of the presentation. And in this thing, we're going to have one mask for all messages, but still, we need to have some randomness, right? We want to have the security. And so to ensure this, we're going to change the keys. And so for all the messages, we're going to change the keys. So of course, I mean, if we have like 1,000 messages, this is not working like that, right? So we can batch some of the messages up to some sizes, and then we are going to have a new mask and this kind of thing. But we are able to batch a few messages in the same thing using this kind of assumption, right? Just a notation, so we're going to have like the blue box to represent the mask, and then we're going to have the keys represented like with the color full boxes with the keys in there. So we're going to use this kind of notation in the rest. So the first thing is like this assumption is not new at all. So the security can be reduced to LWE, and this is not new. There are many papers. From time to time, this is called like the share A. There has been a presentation at Eurocrypt previous year, this kind of thing. So we have the security from this, and we know this is secure, which is kind of a good first property when we are trying to build cryptography upon this. The second thing is like, we have also the inherent linear morphism, right? We are also using scalar product, inner product, and this kind of thing. So there is no reason why we should not have this kind of linearity in the ciphertext. So we are able to compute the sum pretty easily. This is kind of the same way of doing it with the classical LWEs. Okay, so that's good. The thing is, what we want to do in here is build a bootstrap. And so let's have a look on how to do that. If I'm taking the thing from super far, a bootstrapping is like an homorphic decryption, right? So first thing is, let's have a look to how to decrypt everything. If I have a classical LWE, the goal for me will be to remove the part where the A so the mask and the keys are together, right? And so just by removing this, meaning I'm computing an inner product, and then just do the subtraction, I'm going to get this. This is working exactly the same way for the CM LWE, right? I just have to do like multiple inner products to remove all parts with the keys. But this is basically the same thing. And the good thing is like, this is a purely linear operation, right? This is an inner product, so purely linear. So we can try to do this in the homomorphic world, meaning that we are going to encrypt the key, and then we can remove this kind of thing. So what we have, so I'm abusing slightly notation in here, but the thing is what we have our plaintext, and this is the input, and then we're going to have each part of the key that is encrypted. And then I'm just going to compute like an inner product with each of the good part, and then what I have is not at all a bootstrapping. The thing that I've done in here, in the end, is just changing the encryption key from the ciphertext. And so what is called? This is a key switch, right? The thing is, I'm going from the key, which is with the S1, to the S1 tile, like with the prime stuff. And this is the only thing that I've done. So just going through a partial decryption is not enough for a bootstrap, right? And the worst thing is, like, when I'm doing this kind of thing, then the noise has increased, and I'm super far from bootstrapping, where the goal is to reduce the noise. So our goal in here is to be able to compute a real bootstrapping, right? And so we have like an homorphic decryption that we have to compute. And the part in here is we need to remove the error in the this. And so what it means is, like, to remove this error, we need to be able to compute a rounding function over the message and the error. And this is the way to go. So we're not going to be super far to take the technique, and the thing that we're going to do is take the TF-HE blueprint and trying to see if we can match this with the CM assumption, right? And in TF-HE, the thing that they are using is a bit more than just the LWEs. They are also using the ring version of the LWEs. So basically, this is all the same thing, but we are going to use some algebraic structure in there, and meaning that we are going to work with polynomials. So everything is the same, but we are using polynomials instead of the scalar values, right? And we are going to go a bit more in details in the next slides, but basically the way of thinking bootstrapping is like we need to compute many, many products. So we need to have an efficient way to compute such kind of products between polynomials. And so this product is called external product, and the thing, this is done between LWE, so this kind of thing, and the RGSW, that is not really defined in here, but you can think of this as like a set of many, many LWEs. So in the end, you have like kind of a vector through a matrix computation to do, and in the end, you're also recovering a vector. So this is called the external product. Okay, so first question for us is, what can we do to do the same thing using the CM assumption? Basically, this is working out of the box, right? I mean, this is the same slide that you have seen before. I'm just using polynomials everywhere, and I can do exactly the same construction. Also, we have the security and this kind of thing, but this is exactly the same thing. But think of everything as polynomials, right? So if I'm able to have like the CM LW version, meaning like the CM version with polynomials, since the RGSW are just set of LLWE, then I'm having all the good types in here, right? So the last question is like, okay, we have the good types, but is the external product really compliant with just like the CM version of everything? Before going to this hard question, let's start again with just a product, a simple product, similar to the thing that we have seen before to compute the partial decryption, right? So once again, this is almost the same slide than we have seen before. I'm just computing like a key switch, right? And the thing is, I'm having in here all polynomials. And why is this important to show is like if we want to compute an external product, this is basically the same thing, but instead of having only like the 1 and zeros in scalar, we are going to have the same thing with encryptions. And so in here, we are able to compute an efficient product between ciphertexts. When we are using the external product, such as generic operations, the thing is we are using the alpha i's that are equal to the secret key, right? And so this way, I'm able to compute efficient product with the secret key encrypted. And when I'm doing like a sequence of it, I have the bootstrap. So this is kind of the blueprint. So yeah, this scheme is kind of ugly, but this is a good summary of what is done. And so we are starting with everything as a CMLWE. Then we have the function. Remember, in the bootstrapping, we want to be able to compute functions. This is encoded as kind of LWEs. So or I'm just saying LWEs and LWEs. You understand what I mean? This is always the CM version of everything, right? But this is a pain to say. And so I can do the first external product with the encrypted key, with the right version. I'm doing all the sequence in here, and in the end, I'm going to have like all the functions for like the independent function of each of the message inputs for my CM version. And so this is the first part. I mean, yeah, that's cool. So we are able to construct a bootstrap where we have also the freedom and the choice of the function independent of the slots. So this is not like a SIMD way of doing it, right? I can compute any functions on any of the input messages. So that's a first check in our to-do list that we had in the beginning, right? The thing is, now the question is about the performance, because we are doing all of this, but in the end, if the performance is super shitty, then nobody's going to use it, right? And so why is this efficient? Why we are talking about the external product and we're going through the polynomials and all this kind of thing? So the idea is like the external product allows us to work with polynomials, and so with the property of the polynomials, the rotation, this kind of thing. But there is also a huge thing in here. Since we need to do many, many polynomial multiplications, the goal in there will be to use the FFT, so fast Fourier transform. This is the magical trick where all the polynomial multiplications are going to be way faster. And so we are going to use this thing, right? So we are going to the natural domain, to the Fourier one. And then, so the idea is I'm going to have my polynomials input, compute the FFT, then I will be in the Fourier domain, compute the product, this is super cheap in here, and then compute the inverse FFT, and I will have my result of the product in the right domain, okay? Super classical way of computing the polynomial multiplication. And this is in here where we are going to have a lot of gains using our approach. If I'm taking the usual bootstrapping, right, so the one with the TFHE blueprint and the way this has been defined, the thing is I'm going to have my ciphertext and I want to compute some bootstrapping over it, right? And I have my key in here, but my key is not going to move. So I'm going to generate my key, this is my bootstrapping key, and this is fixed once and for all. And so I can pre-compute everything, I can go into the Fourier domain, and this is on the right format. And this is pre-computed, right? But each time I want to compute the bootstrapping, then I need to send everything in there. So everything is each part of the ciphertext in there. And so you can see it coming, right? If now we do the comparison with the CM approach, in here, the part that we have already pre-computed is huge, because we have all the keys for all the slots that are already in Fourier domain, right? And so we still need to compute parts with the Fourier domain, right? We are not able to predict the ciphertext and this kind of thing, but the difference is the ciphertexts are way much smaller in comparison. And that's why we have so much gains using the CM version. And so practically, what does it mean? So these are kind of ugly arrays with all the numbers, but what do you need to remind from that is we are able to have a ×2 using the binary representation, so it's 2 bits input. This is the way to represent booleans with TFHE, trust me on that. And so the thing is, we are computing a key switch followed by bootstrap, which is the fastest way to compute a bootstrapping overall. And so using this, we can do the comparison with the CM and the bootstrap. And so what we are doing is basically taking the time of one bootstrapping multiplied by the number of slots. So nothing is parallelized in there, right? And we compare it with the cost of computing bootstrapping in the CM formats. And so we have up to ×2 better performance using the CM version. And this is true for the usual failure probability and the probability which is generally used to be safe against the stronger security model, which is called the NCP81. Okay. So conclusion. We have something which is twice faster using the command mask. We have the freedom. We have also plenty of stuff that we can do that I haven't talked about in this. We can do compression. We can do also free operation between the slots just because of the representation that we have. That could be super useful. But of course, this is not a wonderful land, right? And so we have some drawbacks. Particularly, the key size are going to be huge. And so the thing is, I'm showing you the ×2 gains that we have on the Boolean inputs. And theoretically, we should expect the same kind of gains for the over precision. Meaning, if I'm going to encrypt 4 bits, for instance, I should have the same gains using the CM version. But this is not true just because of the key size. And so when we're using a CPU, then this is going to just destroy the performance just because of the key size and time to read this kind of thing. So we have questions in here, theoretical, how can we try to reduce the key sizes? And also maybe try to implement on other hardware, just like GPUs, for instance, where the cost of exchanging the data is way much more smaller than on the CPU. And the other thing is that was the motivation of the talk, right? Is trying to compute more efficiently operations over large integers, meaning 32 or 64 bits. And unfortunately, this still has to be done. So if you are any motivated to work on that, just come and talk to me. And on this is done. Thank you.
Thanks for the quick talk. Since we're already quite a bit late, I suggest we take any questions offline, if you can ask the author directly. But we still have time to thank both speakers of the session again.